So, what should we be worried about? If I were to use the statistical way of talking about it, I am talking about something that you might have to get used to. I'm talking about the distribution of the sample mean, and sometimes I call it the sampling distribution. Doesn't it look nice? I would say we should be worried about, and here is some R code, and let's try it. Now let's look at it a bit because it has a bit of color, and then we can jump into R and do it. The core of our concern here should be that we should realize that the average, the mean of the 10 people is not the one and only truth, right? How can we conceptualize this? How can we think about this? We can think about this in a way that if I did a new sample of 10 people, right, in the other auditorium or even in here or wherever, I would get a different value for the, first of all, for all the 10 heights. They would not be the same heights, right? I make a new sample, I get 10 new heights, I compute the average, and it will give me a different value. I'm positive I will not get 178 if I do it again. Really low probability, strictly speaking 0 to get exactly that number. And so we should think about what could happen. What could happen if I do it again, and maybe again, and again, and again, and again? How different could the mean be if I redo it? That is what should tell me how good the single number is, right? If I can convince myself that if I do it again, I get basically the same number. Exactly, I never do. But if I get more or less up to what I'm interested in, a precision that I'm happy with, if I get basically the same thing again and again, if I could let my theory convince me that that is going to happen, then I know I have a good number to use, right? It has a low noise, it has a low uncertainty. But how the heck could I know that? Either I need to spend a lot of money to redo my experiment 1,000 times, and then after having done it 1,000 times, I realized, whoa, I could have just done it once, and that would have been fine. So I would have wasted a lot of money in doing that. So that's why you take a stats class, to at least avoid that stupid mistake. Here, I show you how we can let R trying to do the story for us as a simulation experiment. I can try to play around with potential new experiments using my R. Today, I just use it as a motivating intro to what I'm going to show you. Then I'll show you some formulas and some math that can solve it for us. And then in a couple of weeks, we'll go back to actually this R approach, the computing approach, because it's pretty strong and heavy stuff, actually. But for today, it's just to make a little example and play around, right? I set up the situation to be exactly the one, at least approximately. I just use a sigma of 12, I use a mu of 178, and I use a sample size of 10, right? Then I start out by, let's just simulate my one set of my data. So I use the R norm. I take 10 normal distributed random variables with the right mean and standard deviation. So I simulate my sampling of 10 people from the room here, right? Let's jump into R now. So I'm still talking about the challenge we have and thinking about how we could potentially solve it to get to my interval that I already showed you, right? So that's the structure of today's activity. So let's try to simulate. Here were 10 sampled, normal distributed heights. If I only have 10, yeah, I can do a histogram, but it's not really of much value to do a histogram of 10 observations. It can be done, but it's not really very helpful. I could compute the mean and the variance. Well, the mean was pretty close to 178 this time. Was that pure luck, or was that just as it is? If it's like that, maybe 10 is a pretty good... let's try to do it again and see what happens on the mean and the variance. 178, that was pretty close also. Let's try again. Ah, 170, no, it can actually vary quite a bit, 174. Can you follow me? This is the exercise we should do to know about how good is one average of 10 people. I should start thinking about how could it come out, right? How good is it? How precise is it to tell me what's going on? Have you followed the numbers? Well, that's a bit of, if you sit and do like that on the computer and you find that is useful for you, maybe you should again let your own brain activity start a little bit and think, hey, maybe I could get R to do this for me, where I don't have to stand and do like that again and again. It's a computer program. Computer programs are very good at repeating things for us. So let's try to see if we can repeat that many times. And I'm quite modest here. It repeated 100. The computer would not complain if I put 1,000,000 there, actually. So it's pretty easy to repeat it many times. So I repeat it. I replicate 100 times. I take 10, right? I put it into a matrix, and then just a little bit of R thing here. There is a little function that can take a matrix that I have in the mat. That's my 100 by 10 numbers. I compute the mean for each set of 10, right? I have 100 sets of 10 observations. I compute the mean for each of those 100. Here they are, 100 means. So I've done it 100 times in a single snap like that, right? And I could do 1,000,000, but then I don't want to look at them. Now it becomes interesting to do the histogram, actually. Now I'm doing a histogram on those repeated means of 10 observations. That is the important histogram. That tells me, when I compute the mean of 10, it could be anywhere between 170 and 185 something, right? That's more or less the interval. That if this is the truth, if this is what I have, that is what can happen, right? This is the interval we put into a formula in a second now. We should be worried about the mean, actually, of those repeated means. What would that be? All of us would guess 178, and yes, it is, which tells us, actually, that the mean is a good choice to estimate the mean. Right? The average of numbers is a good choice to estimate the theoretical mean of the random normal variable. Luckily, because if not, it was a stupid theory, right? What about the variance? The standard deviation of those 100 means, right? I computed the variance and the standard deviation of the 100 means. Now it's not 12 anymore. The standard deviation, which would be a variance of 144, right? The variance of the means, or standard deviation of the means, are only 4. Rather than 12. The variance, the precision of the mean has become smaller. That's the beauty of statistics. If this law of nature, which it basically is almost, if that didn't exist, I would not be here as a statistician at least, because otherwise we would not have any business to do it all. It's almost a law of nature. That when you average more and more, you get better and better precision, right? When you have more and more observations, the more information you have. Sounds pretty obvious, right? That is what we see here in this thing. So, what I've shown you in a little toy example, simulating example, is a version of this theorem, which is something that we almost knew, actually, but we'll see that. What this theorem tells us in math, it's just what I showed you, that if I take repeated, or rather I should say, if I have independent normal distribution, that is 10 heights that come as normal distributions. I assumed that for now, that they are normal. Then, if I average those 10 normals, actually there's an extra result here that I'm not going to prove to you. This is a probability theory result, that when you add or average normals, they still become a normal. Right? That's a probability theory result. The average of some normals, the sum of two normals, they are also a normal distributed thing. Fine, we're not going to dwell on that. I think most of us would have just assumed that to be true without thinking about it. So that's one of those results. Let's the probability guys prove it to us, and hey, it makes sense, so we'll accept it. What it also tells us is that the mean of the averages is the mu. This is a stupid result I mentioned before. On average, the average becomes the right thing. It sounds a bit silly, but there is actually a little twist to it, right? But the other thing that we saw on the plot and on my variance is what I have also proved and put on this slide here. That's the proof of the mean and the variance statements of the theorem, right? The theorem tells us that, to go back to the silly one, the average of the mean, or the mean of the average, we can use various words depending on how we see it, the expected value of the random variable, which consists of the average of the 10, is the mean of the population, right? So it's a good idea to compute the mean, the sample mean, to estimate the population mean. That's a good idea. On average, it's on target, right? It has no bias. We see it as throwing a dart to the skive dart board. It hits on average. It has the right target, right? It hits on average. It hits the right thing. How noisy is it? How far away from the truth are we hitting by using the mean of 10? Well, that is what we express in the variance of the mean of 10. This variance, and here we use those rules with the airline example that we played around with last time. Now I use these variance rules if I want to prove this little statement, and let's do it because it's a very central thing in all statistics that we see the first time now, that when I average, I take out the constant and I square it, a times x, and a variance to that, that's a squared times the variance of x. I take the sum of the variances, since they are all coming from the same normal distribution with standard deviation 12 centimeters in my example, generally sigma. I add them up, so I have n of them, and since I divide by n squared due to the factor 1 over n, and I add them up, n of them, I get this beautiful, fantastic, dramatic law of nature, that the variance of the mean of something is the variance of the original data or measurement or population, if you want, divided by the n, the number of elements in your average number, right? So the precision on the mean goes like this when n increases. Unfortunately, it's the variance that increases with n. The standard deviation increases only with square root n. So it can be pretty expensive to get high precision, actually. That's just a fact of life. So, to move on towards what has this to do with we're still just using the mean to estimate the mu, right? That's the whole task we are doing today. That's my first slide. I take my 178 centimeters and use it as an estimate of mu and call it mu hat. That's the inference idea of it. And I'm still there in my mind, right? Why is this normal and probability thinking a good idea still? Maybe you got it already, so I'm just repeating it for you here. What I found out now was that the standard deviation of such an average of 10, if I consider it as a random variable, since it is, next time it gets a new value, that looks like that. That's just expressing what I just showed you, but on the standard deviation scale. That also means, and I'm putting just the same thing in a slightly different way just to make a point, it means that since shifting it in a way doesn't change the variance, that's also a rule we saw last time. So, why do I put it like this? It's because we should be worried about the difference between this one and this one, right? Because that's the error we make when we claim that 178 centimeters, that's my best guess of mu. So I try to claim that my number should be mu, right? Or estimate mu. So I should be worried, at least when I'm thinking about what I'm doing, I should be worried about how close to the truth am I when I make this claim, when I make this statement. And when you're out in business, or those of you going to science, when you make a claim, there's either a boss or a management or a board or a scientific community out there or a big population awaiting for your decision on which drug we should use for one or the other, which recommendation we should use for certain security things. You have to think about how close to the truth am I. Well, the good news is that this formula, theorem, result tells us something about how close to the truth we are. It tells us, namely, that we know on average how far away from the truth we are. On average, we are sigma over root n away from the truth. That is a valuable number to us, right? This is really, 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 really nice in our guts. That we can say, not only say, this is my best guess of the world out there, 178 centimeters, and hey, I know on average how close to the truth this will be. This is my close to the true number. So I can give you not only the estimate, I can also give you the feeling of how good it is for us. Right? Here is a second version of the same thing put into another way. It's the same thing that I just put in a so-called corollary, as you say in math, right? That where I put it in a slightly different way. I put it like this. I say that the error I make relative to the standard deviation of the error, right, which was sigma over root n I just found. If I take the standardized error I make, what my result has told me is that such a standardized error I make in using my mean follows a standard normal distribution. Now you can see we're getting close now. Now I have a very specific distributional probability model framework linked to what I'd like to do, linked to using the mean to estimate mu, right? So now I'm very close to being able to do the final result, where I can tell you how can we use this probability insight, because the standard normal we know, right? We know the probabilities, so we can use those probabilities to make the right statement, combined with our knowledge of the variance, the very joyful knowledge there. However, we have a problem. Houston, we have a problem. So this is where I think, let's see, I'm trying to find the right place to make the jump. I thought it was going to be there. No, we'll keep on this and then we'll jump after this slide. Okay, sorry about that. In order to make the last step, we have a problem. First of all, the problem is how should we transform this into the interval? Well, I showed you a result, but it's actually not quite this is coming exactly from here. Because the problem is this stupid sigma is in my formula, right? I'd like to give you a formula that we can compute to find the interval for the mean, right? All my theory here includes the sigma. You have to know the sigma to know the error, right? So we have to know the sigma. It's a bit annoying, actually, that we have to know the sigma. Or maybe you think, hey, what bigger problem is that? I think I know sigma. You would, if you thought like that, you're doing pretty well. Why is he so worried about that he doesn't know sigma? Because I know sigma. I can compute a sigma from the data, right? And yeah, hell of a good idea. Makes sense. Let me compute the S as an estimate of sigma. As an estimate of sigma. This is not sigma. This is our best guess of sigma. So, Houston, we have a problem if we want to be mathematically rigorous now. Because all my results actually, that I showed you this normal and then I divide by the, these were rules that talked about a normal distribution and using variance, blah, blah, blah. It breaks down when sigma, because all of these computations were as if sigma was a known number, just using sigma as a constant. But sigma, when we do it like this, and using the S is of course what we have to do. It's the only thing we can do because sigma is not given to us by God in any way. We cannot go into the world and do statistics relying on some God or whoever we believe should give it to us. No one comes and gives you the sigma for free. Just in any cases, you have to find it yourself and compute it yourself. So, we have to turn back to the theory a bit and challenge it. And the probability theory guys, and let them help us. And whoa, luckily, they did it for us. They can handle it. So we make the shift to this fantastic no, I'm actually sorry, Gandalf. Can you undo the shift? Sorry about that. I've messed up, but that's not to worry about you. We'll fix it afterwards. I'm still not done with this great thing. Here is the more applicable, but also involving a new thing to you. Here is the applicable version of the same thing that I just talked about. The applicable version does not use sigma in the consideration. It uses the computed standard deviation, S. And here I consider it with a capital S because we have to face the additional challenge of the sigma itself being a noisy estimate, right? The S is not the true sigma. It's different from the true sigma. I'm sorry, it's a step up in abstraction, but that's how it is. A computed S is not the true sigma. So the same problem goes for that one, actually. But I'm not so worried about that. That's not my key purpose right now, my main focus. My main focus is still the mean, but I'm just challenged of the fact that I would like to know the true sigma, but I don't. I have to compute the S. Well. Probability theory people can then show us that such the right standardized error I make in using the mean to estimate mu is given not by the normal distribution, but it's given by the so-called, here you see it and here the first time, the t-distribution. Or I should be more precise because there are many different t-distributions. I should say the right t-distribution going with exactly the number of elements in my mean. And we call it the t-distribution with n-1 degrees of freedom when it's going to be used for the mean of n. That's how the theory goes. Here is a difference between the mean of, the t-distribution with 9 degrees of freedom and the standard normal. That is my reason for all the fuss. Are you not happy now? I hope you're happy that I gave you the red one instead of the black one here. What would have happened if I stick with the black one and just say, hey, I don't fucking care about this S and the sigma thing. I'll just use the S as if it's the sigma and forget about all that trouble? Maybe sometimes not too much, actually. However, be careful. Be careful for small numbers because the difference is out here in the tails. The difference is in the tail probabilities, actually. The t-distribution is wider. Can you see that? The red one goes further out. It has more probability out in the tails. There are more uncertainty being taken into account when we use the t instead of the normal, actually. For instance, for taking the 2, can you remember the 2 in the standard normal? That was 0.0223, less than 2.5%. Can you remember that? We found that probability last time. Now, if I go for that probability, it was only 0.0223 in the standard normal. Now it's 0.038. If you want to push it a little bit, almost twice as big, at least 50% as big. So relatively, the small probabilities can actually be quite affected by whether we use the standard normal or the t. Yeah, here was the normal that we looked at last time. So now we make a shift to how we can use that to actually provide